So we were just looking at encoding letters in the English alphabet, and we were talking about using block coding to try and get down to the maximally efficient code lengths, and then we were talking about doing something better by actually properly jointly encoding letters. To think about how to do that, we now need to turn our attention to the joint entropy. So we can consider the joint entropy of a multivariate. For example, let's consider variables x and y jointly. So here, what we can do is, it's a simple, straightforward extension of the entropy to a joint variable case. You can see here that in all the mathematics, we're now considering x and y together. We're considering joint probabilities. We're doing a joint Shannon entropy, Shannon information content, I should say, on the two, and we're summing across the total state space that we have here. Of course, our joint entropy is equal to the expectation value of the Shannon information content of x and y held jointly. And our interpretation is a straightforward extension. The surprise of a symbol x and y, or the uncertainty for variable big X and big Y, is simply that of the joint sample x and y taken together. So here we simply think about pairs or higher order sets of events. Let's think about the game of Guess Who. So we could ask, what's the Shannon information content about finding out that somebody's hair was blonde in the game? We then might think about a joint set of events. We might say, what's the Shannon information content of finding out that the person's hair is blonde and their eyes are blue? We could also ask about the variables themselves. What's the average uncertainty in the hair color? Or we could ask about what's the average joint uncertainty in the hair color and the eye color together. Okay, so the joint entropy is a straightforward generalization of the Shannon entropy and Shannon information content to joint or multivariates. So it has all the same properties, only the variable is multivariate. As I say, that's a straightforward extension. We've written everything down with pairs of variables x and y, but of course we could have more variables than that in there as well. Now, one key question is, let's just concentrate on a pair for the moment. Is the Shannon entropy of the pair equal to the sum of the entropy of each of the values here? The answer is no in general. This is only the case where our variables are independent, which means that the joint probability is equal to the product of their individual probabilities. This is what independence means. But variables aren't always independent, right? Let's think back to the example we were just looking at with letters from the English language. If we look at a sequence of letters, and we might now start to think about the joint entropy of pairs of letters that occur together in the sequence. Are the individual letters there? Is their occurrence independent of each other? We know the answer is no, because there are pairs of letters that occur far more frequently together than they do on their own. For example, a Q and then a U. Once we see a Q, we are almost 100% certain that a U is going to follow it, right? So there, we are not so surprised when we see the U. If we encode their surprise together, it is not equal to the sum of the surprise in seeing a U plus the sum of surprise in seeing a U. Okay, the joint surprise is not equal to that sum. It is less than that. And we'll think soon about what the meaning is of it being less than that. We'll skip over the coding exercises. You'll do those separately. The last thing I want to mention in this short video is about where the Shannon entropy comes from. And we can talk about this now since we've seen the joint entropy. So what's really important about our equation for Shannon entropy and our equation for the Shannon information content is that these are unique forms that satisfy three specific axioms. They are that the entropy is continuous with respect to small changes in the underlying probability distribution function. Okay, that's really important. We shouldn't see large jumps in the number of bits that we need to include, discontinuous jumps in the number of bits that we need to encode our variable if there are small changes in the probability distribution function. What we also have is that the average Shannon entropy monotonically increases as the alphabet size increases if we have equiprobable symbols across that alphabet. Okay, and the last axiom is what's known as grouping, which means that for independent variables, we require that the entropy or the average uncertainty is equal to the sum of uncertainties across those variables. Let me emphasize again, that's just for independent variables. That makes sense, right? If our variables are independent, then the total uncertainty should be a sum of each of them, because learning about one doesn't tell us anything about the other one. Now, it's important that just writing down these three axioms leads us exactly to this function and no other. Now, of course, I should point out that it's not specifying the value of the base of our logarithm, but it is specifying the form. Changing the base of the logarithm simply changes the units that we're measuring this in. Otherwise, this is a unique form that satisfies these very simple, straightforward axioms that we're not arguing with. Okay, so this is a unique form for what information is.